focus on is how do you architect a system that allows you to work around a delay instead of stand behind it?
Yeah.
Which really
Yeah.
takes us to queuing theory.
Yep.
Right? Which is another large part of your book, and I'll get back to batch size in a second.
Yeah. And non-intuitive part for most people.
Exactly. But you know, it's non-intuitive, but innately we all understand it. If we've ever been to Costco on a Saturday or stood in a fast food line, we all engage in queuing theory every day. But it's kind of eye-opening to think about what we innately understand, but apply it towards our process flow, especially when we think about designing, the work product being invisible within design. Can you speak a little bit about that?
Yeah. I mean, I often, the most accessible example of queuing theory that has, I think, universally worked for me to end up explaining, how queues work to people is traffic at rush hour on a crowded highway. And sort of, I make I use the analogy, I say, okay, so you're already familiar with queuing systems. Let's take a 4-lane highway. I remove 1 lane of capacity at rush hour. What will happen to cycle time? I've removed 25% of the capacity. Does that mean cycle time goes up by 25%? No, it doubles or triples.
Yeah.
And then I say, okay, what happened if I removed 25% of capacity when the system was lightly loaded at 3 a.m. in the morning? No change in cycle time. So I say, okay, so your intuition says that in a queuing system, changes in loading have a nonlinear impact, and that nonlinearity depends on capacity utilization. Okay, so now let's look at what you're doing in engineering. Engineering is another queuing system, variable arrival times, variable work content. It classically matches everything you would analyze in a queuing system. So how do we behave in engineering? We say, well, if I put 10% more work into engineering, it should take 10% more time.
Doesn't work that way.
Is that we'd want to operate as close to, a perfect engineering organization would have no engineer idle for more than 5 minutes in the course of a year. Then we would be doing a brilliant job in managing engineering. When in fact, what you're doing is you're guaranteeing your resources are going to be blocked 99.9% of the time. So if any variability at all showed up, your ability to dispense with, to make that queue go away is very limited because you have zero margin left in the system. And I think it's a huge mindset shift change for a lot of engineering managers to realize that you have to you get your best economic performance when you build capacity margin into an engineering organization. And when you focus only on high utilization of the engineers, what you're silently doing is you're creating work in process. You're creating work that cannot be serviced sitting in queue.
Right.
And when you take into account the cost of that work sitting idle, because that work has a cost to delay. If 95% of if 70% of your cycle time was work sitting idle waiting to access an engineer, that's costing you cost to delay dollars in the process. So chasing after that last 5% of engineering utilization is a disaster with respect to queue time. In fact, when you look at the math, basically, if I were to take the capacity utilization rate of an engineering process, as I move it up from 80 to 100%, as I move it from 80 to 90, I double the size of the queue. It's basically, the formula is rho over 1 minus rho. But the key thing is every time I have the distance to the 100% point, I double the queue. So I move from 80 to 90, I double the queue. 90 to 95, I double the queue again. 95 to 97.5, I double the queue again. And so I see this astronomical rise of queuing effects as I take even very small steps towards high utilization.
But it also reflects a very linear low impact if you have low capacity. So I would assume that
Right,
there's an
the-
inflection
the-
point
the,
that's
uh,
optimal.
The efficiency gains are minimal when
Right.
you're operating there. But no, you're absolutely right. It's a U-curve optimization.
Right.
That's one of the great blessings when you look at these problems quantitatively is you discover there invariably are these U-curves where there are two competing costs that are finite. It might be a hyperbola against a linear function, or it might be a geometric function again. But you see these
You added them,
U-curves,
yeah.
and the great blessing of a U-curve is you don't have to find the right
have
answer.
to be exact.
You,
There's that-
you don't need the right
As
answer.
long as
If
you're somewhere in the bottom.
anywhere in that zone, in that optimum zone, you could be 10% either way, and it makes a difference of 1 or 2%. So people tend to think these problems have to be very accurately analyzed at
Right.
things until they actually analyze them and they discover that they don't have to be.
Right. So, looking at queuing from a bit of a different perspective here, you talk about, and you have this nomenclature for, a FIFO, a very serial first in, first out queue, a first in, multiple out queue, or multiple in, multiple out. For our listeners who are thinking about process flow, is there an optimal queue architecture, or how do you decide or think critically about what is the right way to think about? Should I have a matrix organization of engineers with a couple of programs? Should I have cross-functional teams? How do I build a queuing system that also in and of itself doesn't create more work in process queues?
Well, you're actually asking multiple questions.
Yeah, I'm
there,
terrible at that.
and-
Yeah.
and things
We've got
in
all day.
terms that
Yeah.
have the potential to get entangled into an answer. I mean, there are some general principles in queuing where what you would want to do if you had 5 servers and you were asking, should I have a queue of work in front of each server, or should I have a common queue, shared queue, serving all 5 of the servers?
Right.
And mathematically, that's a fairly straightforward problem because the shared queue has less intrinsic variability than having dedicated queues for each server. Now, everybody's experienced that at an airport where
Right.
they'll
TSA
go,
or something.
they'll end up having multiple lines. You're never going to pick the right line
Right.
and things like that. But intrinsically, what happens is, let's say you have these isolated lines, at the ticket agents, and one customer wants to pay for their ticket with pre-war rubles and things like that. Everybody in that line ends up incurring a large delay associated with it. When you have a single queue with multiple servers, that one bad job blocks a single server,
But not
but
the
it doesn't
others.
affect everybody else in line.
So what would that look like in an engineering development process? Is that, so I have the need for mechanical engineering. So it would be better for me to recognize that there's a need for that service and have a variety, more in a matrix form of 5 MEs, as opposed to having 5 teams each with a 1 ME. Is that kind of where that?
Yeah, there are times when you do it
Either way, yeah.
A lot depends on what is the variability of the demand for that service.
Got it.
If you pretty much have a constant core demand for the mechanical engineer on the program, enough work to keep the guy full-time busy, either working or working ahead, the guy or the woman, then probably putting the person on the program is going to be the optimum thing to do. If you've got real variable bursts of demand, you'll actually get better performance by aggregating a group of people and sort of pulling them on
Yeah,
demand.
more of a
to
matrix
the
kind of a
program.
thing.
More
A pool.
matrix thing. They're not sort of an overall answer to that. And you'll see that, you'll have people like, you'll always have engineering organizations that have some of these specialist skills that you do not want to replicate on every team. Like user interface is a classic one that shows up in software. Do you want a world-class user interface person on every one of your Scrum teams? Idiocy to do that.
Right.
Not only do you not want to incur the cost, but you're going to end up having divergent approaches. Your products will look like they're designed by different companies. So you'll always have situations where you say, it is better for me to centralize this discipline. The killer in most cases of centralizing resources gets back to the metric question as well. Because classically, the centralized resources are being measured by efficiency, which causes them to operate at a very high level of loading, which produces a disastrous response time for the projects.
Right.
Now, I was working with one medical device company. They used to have a tooling shop, and the tooling shop manager was measured on the cost per tool produced for the various projects. The tooling shop manager didn't want to have extra equipment because it raised his overhead rate. He didn't want to send work outside because he liked having a backlog to keep himself busy and things. He didn't want to use overtime because it raised the cost of the tools. So they said, let's look at what the real cost of the tooling is to a program. The real cost of the tooling is how much it delays our program. So let's shift the metric. Instead of measuring the cost of the tool, let's shift it to how much time you're on the critical path of the program.
Right.
So they changed the metric. They didn't change the tooling shop manager. All they did was they changed the metric. Well, the tooling shop manager said, now that I've measured on how much time I'm on the critical path, I'm going to do things differently.
Right.
I'm going to put in another machine tool. I'll send work outside when I'm overloaded. I'll use overtime when the backlog starts building up. And in fact, I'm going to start visiting these people who are requesting tools for me and ask them, can you tell me the rough size of the part you're asking me to make a tool for so I can procure the tool steel ahead of time so I don't have to wait for a lead time on that material. But the interesting thing is, once you shifted to a sensible metric, this dysfunctional behavior of the centralized resource is not responsive went away. And Microsoft did that in software as well. Microsoft would have expert software groups that are servicing many different programs and things. They created what they call service level agreements, SLAs, where they said, we're going to answer we're going to answer, on average, we're going to answer your questions within 24 hours. No more than 5% of the questions are going to take 5 days to answer. And then that service level agreement became a tool for them to talk to their boss about how much resource do they need. We say, now that the work has gone up, we're not meeting our service level agreements anymore. We need to add more capacity.
Right.